Okay, I'd like to talk about exponential growth. A little of this is a review. We've got an initial value A, let me blow this up just a bit, times your base and to the exponent x. Okay, remember in exponential functions, A can be anything but 0, can't be 0, it can be a negative, positive, but your base has to be greater than 0. And it cannot be 1. Okay, 1 to any power is just 1, so it's kind of pointless. All right, A is your initial amount. All right, so we're going to have decay if B here is a fraction. So it's got to be greater than 0, but can still be greater than 0 and less than 1, like 7/8, 1/2, etc. So A times B to the x equals decay if B is less than 1, but still greater than 0. And it's going to look like so. All right. Now, if B is greater than, oops, I messed up here. Okay, all right, so we're going to have this A times B to the x is going to be growth if my B is greater than 1. Okay, so both cases, B is greater than 0, but if B is greater than 1, it's growth, and your function looks like this. Remember, domain, x can be anything, negative, positive. A negative exponent is still, it just makes this a fraction, positive number still. Okay, notice your domain, your domain is all real numbers. Notice your range for decay or for growth. It's your output y is greater than 0. Okay, now let's talk about E we discussed this week, last week. The number E is approximately 2.718. We get that by taking this part of the growth rate that we used in interest rates, 1 plus 1 over n, 1 plus 1 over n to the n power, and we're going to bring n all the way up to infinity. Okay, that's what's called the limit. As n approaches infinity, this will approach 2.718. Okay? All right, exponential growth is now, our growth rate B, here's kind of our substitution. Here's my initial amount. This is kind of a scientific formula. My initial amount A at time 0, okay, this growth formula, I want to find out the growth at a certain time. My amount, here's my initial amount. What's my amount going to be after time t? Will equal my initial amount at time 0 times my growth rate, which is e to the, and the growth rate is k. Okay, this whole thing together is kind of my b. All right, so e to the k times t, and t is the time component. All right, it's a growth rate if k is greater than 0. Okay, this makes e to the 0.2, e to the 0.3, but it'll make it a growth rate. Okay, all right. Okay, now it's a decay rate when k is less than 0. Okay, so if you go back to this original formula, my initial value times e to the kt, and k is negative. What's all that does? Let's say k is negative 1. It's still a positive number. It's just 1 over e. Remember, e to the negative 1 is 1 over e to the positive 1 when e is in the denominator, okay? It's still positive, okay? So, basically, when k is positive, this is when your b is greater than 1, okay? And when k is negative, your b is a fraction, okay? So, you have decay rate when k is negative, growth when k is positive, okay? All right? All right, and k is negative in decay, t is your time period, okay? So here's your basic formula we're going to be going off of here, okay? Let's do a growth problem. This is kind of an example from the book. Okay, in his cells of a certain type of cell, then a petri dish, let's say, that are growing in the petri dish, okay? N is what we're going to use for the cells, and n as a function of time equals 100 times e to the 0.045 times t, where n is in grams, t is in days, time is in days, okay? So my initial amount, basically, this is my n sub 0, is 100 grams. That's my initial amount. That would be my n sub 0, okay? Times e, this is growth, okay? So my growth rate is going to be 0.045, or that would be 4.5%. The graph will look something like this. In fact, let me show you. I graphed it. there's the graph. Okay, there's 100e to the 0.045 times x. I used x instead of t because it's a function of x. Okay. All right. All right. So we want to find out what's the population in 5 days. Okay. Well, let's go to our table. We've got this in here. Let's go Control T, and it pulls up the table here. And we'll scroll down to 5 days. And right there, 125.232. You can also plug in what? You go to your function here. Where is this? Right here. And plug in 5 there. You can just plug in 5 and get the same value, and you don't have to go to the graph, okay? How long to reach 140 grams, okay? All right, so how long is it going to take for this to become, this here to be 140? What's t going to be, okay? So if I go to the table, notice when I scroll down, okay, let me get this over here. It's kind of, notice I've got, I'm not sure why it's doing that. Okay, notice between 7 and 8 days, somewhere in there is 140. But we're going to solve for it, actually going to solve for it, okay? All right, so how long, so we set 140. Here's my formula. I'm going to plug in, let's go back here. We'll plug 140 in here, okay? Equals 100 times e to the, let me erase this, it's kind of getting in the way. Okay, 100 times e to the 0.045t. And what do we do when we want to solve for an exponent? You take the log of both sides. All right, so here's my equation. I said my future value is 140 equals 100 times e to the 0.045t. All right. Before I take the log of both sides, remember, I just want to get this base by itself. So what did I do? I divided both sides by 100, okay? And 140 divided by 100 is 1.4, and now I've got e to the 0.045 times t, okay? So we've got this cleaned up. Now we can take the log of both sides, all right? So the log of 1.4 allows this exponent to come down in front, okay? So is notice by taking the log of both sides, the exponents are now a coefficient. 0.045t times log of e. What's the log of e? That's base e. What's the exponent that e is raised? You get e. 1. Very easy, okay? So basically, log of 1.4 equals 0.045 times t, okay? So what do? Divide both sides by 0.045, and that's what t equals, 7.477 days, okay? Later they asked time to double. Remember how we did double? That's kind of like if this becomes 200, okay? Well, here we go. If this becomes 200, we just divide both sides by 100, and you're just going to get 2 equals, okay? All right, just like we did before. So this, if you're going to double something, divide this side, both sides by 100, and that's just going to be 2 equals e to the 0.045t. And the same thing, how do you solve for something when it's an exponent? Take the log of both sides. Log of 2, 0.045, log of e. Notice 0.045t. Okay, that exponent is now a coefficient, log of e. Log of e is now 1. Okay. And log of 2 over 0.045 is 15.4 days is the time to double, okay? All right. Let's talk about decay now, okay? Here's the same formula, initial amount times e to the kt, but k is a negative number now. The exponent is negative. E to the negative k just gives me a base greater than 0. It gives me that kind of like that base that's greater than 0, but it's less than 1, okay? So it's a decay rate. Here's some facts in this example I took from the textbooks. The half-life of the carbon-14 element is 5,700 years. The half-life. That's the time it takes for half of carbon-14 to decay. If you've got 100 grams of carbon-14, it'll take 5,700 years for it to decay to become 50, from 100 to go to 50, okay? All right, this example is based on some burned wood that was found in an archaeological dig in Chile. And and this burned wood had 1.67% of the original carbon-14 in it, okay? And they're going to ask us some problems, but we first need to find the decay formula to answer the questions, okay? All right? So here's my formula, and basically I know that my initial amount is going to become half of what, so my amount as a function of time is going to be 1/2 of that, okay? So basically A becomes 1/2 A, okay? All right, this is what a half-life is. This stuff is decaying. So my initial amount will become half the initial amount. So I'll change this A as a function of T to just 1/2 A of the original, okay? Well, guess what happens? We divide both sides by A sub 0, and these cancel out, right? We're just left with what? 1/2 equals E to the K times 5700. We'll take the log of both sides, okay? I didn't skip the step here. We'll bring that down by taking the log of both sides. This comes down, okay? Remember, the log of E is 1. So the log of 0.5 equals K times 5700. We divide both sides by 5700. Log of 0.5 divided by 5700 equals negative 0.0001216, or negative 0.01216%. I moved this 2 places over for the percent, okay? All right, that's what K is. That is your decay factor, negative 0.001216, okay? All right, so we plugged in, and we didn't even have to plug, we could plug in anything, but when we're doing a half-life, this turns into half of its original. So this will be half of the original, okay? And we knew the time, and we solved for the decay rate. Now I've got an equation. A as a function of T equals A sub naught times E to the negative 0.0001216 times T. All right, now we can answer some questions. Okay. When was that tree cut and burned that we found that carbon-14 from in that archaeological dig? Remember, 1.67% of the original, okay, that's 0.0167, okay, in decimal form, right? If I move that 2 places over, this is 0.0167 in decimal form, okay? So remember, that's 1.67 of the original amount of carbon-14 was found in this. So if this represents the original carbon-14, the amount of the original carbon-14 in the wood, this new amount as a function of time is 0.0167 of that, right? What's 1.67 of the original? Remember, of means multiply. That'd be 0.0167. Turn that into a decimal form, okay, times of the original, okay? So when I plug this into the decay, with our decay formula, we're going to solve for the time, okay? So my original amount decayed, so after so many years, it's 0.0167 of the original. Guess what? These just cancel out if you divide both sides by A sub 0. Okay? You don't even have to know what that original amount is. We just know the new amount is this percent of it, or 0.0167 times the original, okay? So I'm left with 0.0167 equals E to this exponent, right? And how do we solve for an exponent? Take the log. Log of 0.0167 equals the log, and what comes down in front is that exponent is now a coefficient, the negative 0.0001216, okay? Log of E is 1, makes it very easy. Divide both sides by this decay rate, and I get 33,654 years is the half-life, okay? I'm sorry, I did take that back. This 33,654 equals T. That's the time it took for that original amount to become 1.67% of the original amount, of its original, okay? All right, so that's all I have today. That's 14 minutes. That's enough. We'll see you tomorrow.